Okay. Um, so previously, it was actually 2 classes ago, I showed you the technique of separation of variables for solving a problem involving the initial boundary value problem involving a heat equation. So I'm going to revisit that, but we're going to solve a slightly different problem that introduces an interesting complication. But what you'll see is that a lot of the same ideas behind separation of variables still apply, and there's certain similarities between the solutions that we have in today's case versus what we saw before. This will be an opportunity to reinforce some of the key ideas of separation of variables. Okay. Now, because what can happen is the boundary conditions have a major impact on the form of a solution. Like they could determine if the solution u of xt is a linear combination of sine functions or cosine functions, and also what kinds of sines or cosines, or possibly other functions. Here we'll have a very different boundary condition from last time, and we'll see what effect that has. Okay. All right, so the problem we're going to look at, still modeling temperature in a rod of length 1. So we're working on the interval 0 to 1, like before. And in the previous example of separation of variables, the temperature of a rod was fixed at 0 at both ends. This time, it will only be fixed at 0 at the left end at x equals 0. But now at x equals 1, the right end point, we're immersing in a solution of water that is maintained at temperature 0. So that does not fix the temperature of the rod. It only fixes the temperature of the medium surrounding the rod at that endpoint. So what does that tell us about the boundary condition? So this is a boundary condition at the left, like we had before. And here's the boundary condition we have this time. So it's a mixed one that involves both u and du dx at x equals 1. So h is a heat exchange coefficient. Okay. All right. And we saw this boundary condition several class periods ago. That also involves a constant k, which we're just going to assume is 1 here for the defining the flux. Okay. So now I can state the entire initial boundary value problem. So here's a PDE, so that's just a heat equation. And here are the boundary conditions. And then for the initial condition, I'm just going to choose u of x0 is equal to x. Okay. All right. So because the PDE is homogeneous, meaning u equals 0 would be a solution, and also the boundary conditions are homogeneous, they have 0 on the right-hand sides, this is a problem that is suitable for separation of variables. Now, I'm not going to repeat the entire process. You can refer to the notes from 2 class periods ago. That was lesson 5, about how this PDE separates into 2 ODEs. Since the PDE is not changed, the ODEs that we get are not going to change either. Okay. All right, so the 2 ODEs that we have are these. Now, one thing I want to point out: if you look up the notes from lesson 5, so last Wednesday, I had these same ODEs, except instead of mu, I had k as the constant. The reason for the change is that k plays a role in this boundary condition. We're assuming it's 1 here, but I just didn't want the conflict in notation. But in separation of variables, we have t prime over alpha squared t is a constant, x double prime over x is a constant, and they must be equal to that same constant, and we call that constant mu in this case. So our solution u of xt will be a linear combination of functions that are t of t times x of x, where t and x solve v's ODE. So all of that is the same as before. But now your ODE for x of x, the solution of that ODE must satisfy the boundary conditions from the original problem. So those boundary conditions take this form, x of 0, 0, and then x prime of 1 plus h x of 1 is 0. So we have to take this into account when solving this. Now, you may recall from a previous discussion of separation of variables, this constant, now called mu, can be anything, but we have to check what values of mu are acceptable in terms of leading to a solution that will satisfy the boundary conditions and also be physically reasonable. So we can consider the cases where mu is positive, negative, or 0. Okay. So I'm going to step through those one by one. And I did the same kind of thing last time, but we have to keep in mind the boundary conditions can have an effect on that. Okay. So, all right. So here are 3 cases we'll consider, starting with mu positive. So when mu is positive, we can write down a general solution to this second-order ODE. But we can also solve this first-order ODE, have a general solution of that. And it's actually this ODE that's going to help us work with this mu positive case. So that's the solution for whatever mu you have. And the problem is, if mu is positive, we're going to have exponential growth. The thing is, that's not physically reasonable. If anything, we're going to have exponential decay, because we know how temperature behaves, that temperature converges over time, like temperature of an object over time, without the interference of a heat source, converges to the surrounding temperature. The temperature is not going to naturally grow without bound, which is exactly what would happen in this case, and very quickly. So we're not going to consider this. Okay. So we have to keep in mind that these PDEs come from modeling physical phenomena. So in fact, the heat equation should not be solved backwards in time. If you're solving a heat equation as it's written, going forwards in time, the solution exhibits exponential decay, which is consistent with how heat energy behaves physically. But if you run it backwards in time, that means that you're going to have exponential growth, which is non-physical. All right, so we're not going to consider mu positive. What about mu equal to 0? So if we go up here, then we have x double prime is 0. So the solution to that ODE is going to be a linear function, something of this form. Stop that. Okay. Ax plus b. So now we have to make sure that it satisfies the boundary conditions. So if we set x equals 0, we must get 0. So b is 0. And here I need to take the derivative at x equals 1, which is just a, plus h times the value of this at x equals 1, which is a plus b. So if b is 0, then we find out that a also has to be 0. So in this case, that's the trivial solution. So we can't consider mu equals 0 either. The only possibility left, and this is the same thing that happened last time, is we have to consider that mu is negative. Now, it doesn't always work out this way. Like if there are some problems for which, like for example, mu equals 0 does lead to a viable solution. Like if we have Neumann boundary conditions on du dx only. So just letting you know, in these two examples I've shown you, the conclusion is the same, that mu must be negative, but that isn't always true. All right, so now we're going to look at mu being negative. So what happens in that case? So to emphasize it's negative, we write it as mu is minus lambda squared. So this will definitely be a negative number as long as lambda is non-zero. And so then we have this decaying exponential for t of t, and x of x is this linear combination of a sine and a cosine, lambda x. So we have to make sure that this satisfies the boundary condition. Okay, and then once we get that sorted out, we need to figure out the constants a, b, and c, and that's going to depend on the initial data, which we'll deal with at the end. So I substitute this x of x into the boundary conditions. So I set x equals 0. This term goes away. Cosine is 1. And I'm left with c, which must be 0. So there's no cosine term. So in fact, I could just okay. Yeah, sorry. So there's no cosine term. There's only this sine term remaining. So then I can take what's left and apply the other boundary condition at x equals 1 to this. And this equation is what I get because the derivative and the solution are evaluated at x equal 1. So now I can, well, b has to be non-zero. Otherwise, we'd have a trivial solution. So that would mean that everything else, if I factor out b, in fact, I'll write it that way now. This must be 0. So what I can do is rearrange that, and I get this relationship, that the tangent of lambda must be equal to minus lambda over h. Now, this is very different than last week's example of separation of variables, where it was concluded that to satisfy the boundary conditions, we must have lambda being an integer multiple of pi. So we had an explicit formula for lambda. This does not lead to an explicit formula for lambda. We can't just perform algebraic or trigonometric manipulations and solve this equation, because we have a trigonometric function of lambda and here a polynomial function of lambda. It's generally impossible to solve analytically equations like that. So there are infinitely many solutions, but they would have to be computed numerically. If time permits, after I've shown you everything else, I will take a little time to discuss how we would find these numerically. I don't want to get into too much because that's beyond the scope of this class, but we'll see how things go. All right, so for now, we're just going to assume that we have lambda that satisfies this relationship. And I'll be able to show you why there actually are infinitely many solutions. All right, so we'll just forge ahead with lambda being an unknown expression at least, but we can still proceed with finding the solution. So now we have these solutions of a PDE that also satisfy the boundary conditions. So we have Tn of t, that's this decaying exponential from before. And then, because a cosine term went away, we just have this sine term for whatever value of lambda n that we have. So for each lambda n that we find from this equation, this function satisfies the PDE and boundary conditions. All right. So this is all we know about the lambdas at this point. Also, while this equation does have solutions that are both positive and negative, we're only going to consider the positive solutions, because if I put a negative in here, then that would not lead to linearly independent solutions. Because what would happen is, if I have a lambda n that satisfies this equation, minus lambda n will also satisfy this equation. The reason why is tangent is an odd function. Both sides of this equation are odd functions, so that's why we have a relationship. So we have solutions that are positive and negative mirror images of each other. We just dismiss the negatives because sine of minus lambda nx would just be minus this whole thing, and it's not linearly independent. We only want linearly independent solutions because anything else would be redundant. Okay, so we've accounted for everything except the initial condition. Okay. So now we can write at least a form for u of xt. Oh, you know what? Can anyone tell me what the typo is in this solution?
The minus has to be outside?
Yes, it must be outside the parentheses. And it is up here. Just mistranscribed going down there. So fix that. Okay. So we just had to find these coefficients a sub n based on the initial data. Okay. So I go ahead and substitute t equals 0. Now the initial data of initial condition u of x0 is set equal to x. That's what I stated at the beginning. And now we have this. So we need to find an. This basically a Fourier sine series in a sense is going to be equal to x. Okay. All right. So how are we going to do that? By multiplying both sides of the equation by sine lambda mx, if we integrate both sides from 0 to 1. So we have that here, and I've just pulled the summation and an out. So if we can work out this integral, then we're on our way to getting a formula for this coefficient an. And we did this last time where I had sine n pi x times sine m pi x, and it turned out this integral was 0, except when n was equal to m. And now it's very helpful at getting a formula for the coefficients. And we're actually going to see the same thing happen in this case. It's just going to be a whole lot messier. Okay. All right, so this can be handled. And well, if we had a value for lambda n, we could just do integration by parts. So I'm not going to be concerned with that right now. We're going to look at this integral and see what happens first when m is not equal to n, and then when they are equal. So here's what we can do to attempt to work this out. And I'll just warn you up front, it's going to be ugly. Okay, so what I've done to go from here to here is use what's called a product to sum identity. That expresses, because this, as written, cannot be directly integrated. But if I write this product of sines as a sum of cosines, and this relates to the trig identity for a cosine of a sum or difference, these can be immediately integrated. So that's why we do that. So now I go ahead and do that. So here we get the antiderivative. And the lambdas are positive, so this won't be 0. Also, we're assuming m is not equal to n, so this won't be 0 either. So we do not have any division by 0 to worry about. And then we have plug in the limits 0 and 1. Okay. So then I go ahead and do that and plug in the limits, and we have that. Okay. So far not so bad, but just wait. Okay. What I've done here is basically I've put everything over a common denominator, which is lambda n minus lambda m times lambda m plus lambda n, which is this difference of squares here. And this is a numerator we get from putting everything over a common denominator. Okay, now what happened? What I did to go from here to here is I use a relationship stated earlier. This right here. Lambda n can be replaced with, if I rearrange this, actually, in fact, I'll just rearrange it right here. All right. So anywhere where I see lambda n, I can replace it with minus h tangent lambda n. Now, that might seem odd. You think, why would I take this very simple expression and replace it with something more complicated? The reason why is because now, aside from this factor sitting out here, everything in here is trigonometric. So I can use trig identities on any part of this. But sometimes it can actually make things easier to replace with something more complicated.
Dr. Lampers.
Yes.
I think that last line should be lambda n plus lambda m. Give the argument of your sign.
Let's see. Ooh, yep. Yes, it should. Okay. Yep. This should be an M. Okay. Okay, and then up here too. Wait. So I'm trying to find what line it is in the source code. Here we go. Okay. Yep. All right. Thanks for pointing it out, and we'll have to keep an eye out for it in later steps. Okay. So then, all I've done here is just rewrite each tangent in terms of as a sine over cosine. Okay. All right. Looks like I don't see any wrong subscripts in this case. Okay. So then what I can do is I can distribute. So there's a whole lot of distribution going on, and okay. Which results in this monstrosity. So then, and once all this is done, and now we try to simplify as much as you can, all goes away. So it turns out that these sine functions, sine of lambda n x and sine lambda mx, they are orthogonal, just like we saw sine n pi x and sine m pi x were orthogonal if m is not equal to n. So this is what happens. So in this case, this particular relationship between all the eigenvalues, lambda n versus lambda m, also results in orthogonality. Well, now I'm having fond memories of when I would assign students a problem to work out where they have some really messy expression, like far worse than this, and the problem calls for simplifying it as much as possible, and then they find it condenses all the way to like 0 or 1 or something like that, and they would actually be outraged over it. Like, how dare I simplify some expression that turns out to be so simple in the end? I could never understand that, but it's like all this work to get 0. But I don't know, I personally have always found that kind of rewarding. And it's certainly going to simplify our task here of obtaining the solution of this initial boundary value problem. Okay, so as I mentioned, these functions are orthogonal. Now, what about the m equals n case? That will not be quite so messy, thankfully, but we do need to see what it is. So in this case, we just have sine squared lambda mx. So for that, similar to the previous separation of variables, use a half angle formula that introduces this cosine. And this is something that we can integrate from 0 to 1. And it doesn't work out quite as nicely as in the previous case. All right, so we plug in the limits here. What I've done here is used the a double angle formula for sine. So sine of 2 theta is equal to 2 times sine theta times cosine theta. So then the 2's end up canceling. Okay. Really, that's all we can do there. Wait, actually, let's see. Yeah, it's fine. So this is what we get for the integral in that case. So now we can take that into account in describing a solution. So if we go back here, we're trying to find these coefficients an. And what happens is when m and n are not equal, it's 0. So all the terms in the summation go away, except for n is equal to m. So we have am. And then the integral, this final result got filled in here in place of the integral. So now we can describe our solution. So here's our solution, where we have a formula for the coefficient. So just flipping this, and we evaluate this integral here. So at least as long as we have the eigenvalues lambda n, once we have them like computed numerically, then we have a formula for these coefficients an, linearly combining these functions, our solutions to our PDE, and then we have our overall solution, u of xt. So are there any questions on how this was obtained? What I would recommend is, like we could do this later, is compare the solution of this problem, the whole process, like so from these notes to the notes from last Wednesday, which was also separation of variables, just so you can see the similarities and differences. And that would help reinforce your understanding of the separation of variables technique being applied to any initial boundary value problem for which it is suitable. Now, if we are able to approximate some of these eigenvalues, like the first, starting from the smallest positive one, then we can at least get an approximation of a solution Because what will happen is, because of its decaying exponential, as n increases, this will get smaller very rapidly. Depending on the value of t, we could probably get a really good approximation of u of xt by including only a few terms. And I mentioned that in the last separation of variables, where you can try using a very first term as an approximation. It's actually a pretty good one for larger values of t. Some terminology I want to mention. Sturm-Liouville problems. These are closely related to separation of variables. So look at the spatial ODE. This is what we solved in this latest example. Is an example of a Sturm-Liouville problem. And so a general Sturm-Liouville problem is one of this form, where we have some coefficients p of x and q of x, and also this function w of x. That's called a weight function, which is why it's named w. And then we have these general boundary conditions here. So if you were to set like p equal 1, q equals 0, w of x equals 1, then you would get this ODE. And then if you set like alpha 1 is 1, beta 1 equals 0, you get this boundary condition. And then alpha 2 equals h and beta 2 equals 1, you would get this boundary condition. So some terminology. This ODE would only have a solution that satisfies the boundary conditions for certain values of lambda. So those lambda are called eigenvalues. And then the solutions that we get, the y of x, that is called an eigenfunction. So this is closely related to eigenvalues and eigenvectors that you'll learn about in linear algebra. So what we have is, for an eigenvalue, we have a linear operator times y is equal to lambda times w times y. So this is like a generalized eigenvalue problem for matrices. It's just dealing with linear operators on functions instead of matrices multiplying vectors. So like we have discrete and continuous versions of this eigenvalue problem. And what's known about Sturm-Liouville problems in general, this problem, is that we have a countably infinite set of eigenvalues that satisfy this equation and boundary conditions. And what we also know about general Sturm-Liouville problems is whatever solutions we get, the eigenfunctions that go with these eigenvalues, so y1, y2, and so on, they're orthogonal. And what that means is this integral from 0 to 1, the domain of a problem, of a yn times yn times the weight function w of x is 0 whenever m is not equal to n. So that's very helpful for finding solutions to initial boundary value problems that are linear combinations of these eigenfunctions. All right, and as I mentioned, it's a weight function. This ODE has a property being called self-adjoint, and the upshot of that, I won't get into detail on that now, but the main consequence of that is that it guarantees that these eigenvalues for which there exist solutions are real. What's also known is that if p is positive and q of x is at least greater than or equal to 0, at least non-negative, the eigenvalues are not only real, but they are positive. So what we can say is that this differential operator, which comes from this Sturm-Liouville problem, is positive definite. So in general, a linear operator such as this, that is self-adjoint and positive definite, in other words, has positive eigenvalues, is sorry, the linear operator that has positive eigenvalues is positive definite. And this is closely related to, especially those of you who are taking 610 now, the notion of a symmetric positive definite matrix. So a self-adjoint operator is similar in spirit to a symmetric matrix. Positive definiteness of an operator, linear operator, is closely related to a matrix being symmetric positive definite. In both cases, you have strictly positive eigenvalues. Okay. All right. Okay. So having positive eigenvalues is quite helpful in that it can help ensure that the solutions that we get to these kind of initial boundary value problems involving a heat equation will have physically reasonable solutions. Because it basically guarantees that in a series solution like this one, that we will always have exponential decay, not exponential growth. Okay. So questions about what we've seen here? One thing I want to mention here regarding this equation, I'm going to introduce this notation. All right, so this operation of taking these functions yn and ym, multiplying them also by the weight function, and then integrating from 0 to 1, the domain of a problem. The inner product that can be defined for any two functions, but here's the inner product of y and ym. Satisfies this relationship. The inner product of functions, which is generally defined as an integral over some domain of their product times the optional weight function, which might be just 1. That is analogous to the concept of a dot product of vectors in n-dimensional space that you would have learned about in calculus. So I try to draw these connections between concepts that you're seeing here for functions as opposed to related concepts like dot product or eigenvalue of a matrix that apply in a discrete setting where you're dealing with linear operations applied to vectors in n-dimensional space, because it's helpful to be able to go back and forth between these continuous and discrete worlds. And certainly in numerical methods, it's very important to be able to do that. So this notation allows me to give an equation that defines positive definiteness. Whoops. Dang thing. That this inner product, if I take, let me include the brackets. If I take a function u that has to be non-zero, u, not y, and I apply this linear differential operator L to it, then take the inner product with u, where that inner product is defined here, it's guaranteed to be strictly positive. So that's what it means for an operator such as this one to be positive definite. And I'll just add a note here that a symmetric matrix A is positive definite if the dot product of x with A times x is strictly positive for any non-zero vector x. I'm hoping it's especially helpful for those of you who are currently taking 610, where we're dealing with this and how it relates to this. Okay. All right. Questions about any of this or about homework?
I have kind of a stupid question about the wording in the homework.
Okay.
In lesson 6, number 1, we're told to transform the problem into homogeneous boundary conditions. And then in number 3, we're told to transform into a new problem with 0 boundary conditions. Those directions are the same, right? When he says 0 boundary conditions, he's referring to homogeneous boundary conditions.
Yes.
Okay. I just wanted to make sure we weren't completely eliminating boundary conditions.
Oh, I see. I see what you mean. No. Yeah, it's kind of sloppy wording on the author's part there. Yeah, because the boundary conditions will always be necessary just to ensure a unique solution. Okay. Other questions? Since we have some time, I want to take, hopefully not too much of it, let's talk about how we'd actually get the eigenvalues lambda n for this problem. And for that, I'm going to have to go over to MATLAB. So I'm going to have to unshare and reshare. Okay. Okay. All right, so I'm totally doing this on the fly, so hopefully this won't go wrong. All right, so the eigenvalues satisfy this relationship. So L, which I'm using for lambda, is the eigenvalue, and that's equal to minus h times tangent of L. And for this numerical demonstration, I'm just going to make it easy and assume that h is equal to 1. Okay. So what I'll do, and hopefully the scaling on this graph will be okay, I'm going to define a vector of x values. Let's see, I'll just go from 0 to 10. I want a lot of points, though. Let's say 1,000. Okay. And then I want to plot x and then minus tangent of x. Okay. That's kind of weird scaling. All right, I'm going to have to condense this quite a bit. So I'll set the axis limits to 0 to 10 in x and also 0 to 10 in y. Let's see how that looks. And that behavior I saw on the graph was expected just because tangent goes off to infinity, it has these vertical asymptotes. So here I've zoomed in on tangent x and y both between 0 and 10. So now I'm going to plot on top of that the line y equals x in red. Okay. All right, I'm going to make this bigger. So, okay, here, and here are eigenvalues. Oh, good, it's keeping the dots there. That's helpful. I'm now notice based on the graph, we also have intersections here, and here. I'm not counting those because that is a direct result of the asymptotes, the vertical asymptotes in tangent. Because what MATLAB is doing is it has a value going off to like minus infinity, and then it connects the dots to the next point that's coming down from plus infinity on the other side of the asymptote. So these vertical blue lines are not actually part of a graph of tangent. So you could almost think of them as marking where the vertical asymptotes are. But these points, let's be able to get rid of these. Whoops. Okay. Oh, okay. Yeah, so the ones I've actually marked here that have these x and y values, these tips that MATLAB calls them, those are the first 3 positive eigenvalues in the case where h is equal to 1. So can anyone tell me, now this is something you would have seen elsewhere, if I'm going to try to find these values numerically, can anyone suggest methods that could do that? Certainly some of you in this class have seen them in the classes of mine. So some of you may not know, and that's perfectly okay. I'm just taking my chances here, but there's a few of you at least who should know.
It starts with a T, doesn't it?
No.
No. No. Or not Chebyshev. No.
No.
No. Lord, I don't know.
Okay. Well, and you
again?
haven't taken that class, I don't think. Anyone else?
What was the question again?
What would be a numerical method for solving this equation? So if I put the equation back, I need to solve this equation. So basically, I have it's a nonlinear equation, so it cannot easily be solved. So how would I solve it numerically? Well, there are several methods for doing so.
Can we use like a eigenvector stuff for that equation?
No, that wouldn't be helpful here. How do you solve a nonlinear equation numerically?
Does it involve iteration?
Yes. What will be one of those iterative methods?
Could we just use Newton's method?
Yes, that is one of the methods. And those of you who took Math 461 or 561 from me last spring would know that. So yeah, there's chapter 10 in my book. It's not a textbook for this class, but anyway. There's a bisection, there's a fixed point iteration, Newton's method, secant method. Those are the ones covered there, and then there's quite a few more variations. So one of the convenient things about this problem is we can take advantage of the fact that we know a tangent has these vertical asymptotes at odd multiples of pi over 2. So here's one at pi over 2, 3 pi over 2, 5 pi over 2, and so on. Furthermore, if we look at, let's suppose we focus on the behavior of tangent, or minus tangent really, between this asymptote and this one, or between any two asymptotes. What's the derivative of tangent?
Secant squared.
Secant squared, always positive. So this is minus tangent, so the derivative is always negative. The function is always decreasing between two asymptotes. What does that tell us? That, well, first of all, we know it's coming down from infinity, going down here, and then it'll be decreasing off to minus infinity. So it covers, the y values cover the entire real number line. Therefore, so it's because it's going from positive to negative, there will be a solution. Furthermore, the solution will be unique because it is always decreasing. We know there will be exactly one solution of this equation between each pair of vertical asymptotes. So what you could try, for instance, is now a slow way to get to solution would be, like, if we focus on this interval, you can use bisection because you know a solution exists in this interval. But yeah, that would be really slow. Or you could use a faster method like Newton's method, and maybe as an initial guess, choose something that's close to the asymptote, or maybe like use a midpoint or something like that. And then as long as you make sure that your iterates stay within this interval, that's called safeguarding, then you can ensure that you'll eventually get to a solution. So numerically speaking, this is not so bad because you're able to at least bracket the solutions. That's something that's very helpful. Okay. So I just wanted to highlight that. It's a bit out of the scope of this class, but it's the thing is, especially when you get to higher level, there's all kind of connections between topics that you see in different classes, and just like what I was showing you earlier, there's a lot of connections between what we're seeing for initial boundary value problems and basically spectral theory of linear operators, which closely relates to linear algebra and the eigenvalue problem for a matrix. And there's a lot of concepts that are closely related, just defined in different settings. But being aware of that can help you to understand them in whatever setting you're in. Okay. Okay. So, all right, that really is all I have for today. But does anyone have any last questions? Well, I know my brain is fried after just doing this class and a previous one, but and that applies to several of you too. Okay, then I'm going to call it good. And so good luck with ongoing homework. Be sure to shoot me an email for any questions, and I'll be available after 4 o'clock tomorrow here in Teams if anyone wants to chat with any questions. So good luck with all the things. I'll stop recording here.